Ian Smith from MIPI Alliance, and I'll be your moderator for today's session. So today we're presenting the final webinar in a series of 3 MIPI audio webinars taking place this week. In the series, the leaders of MIPI's audio and software working groups are presenting the full portfolio of MIPI audio specifications, providing an explanation of each specification and sharing their insights into future developments. Tuesday's session provided a primer on all of MIPI's audio specifications, giving a high-level introduction to the MIPI audio interfaces and all the supporting software specifications. Yesterday's session zoomed in on MIPI SoundWire i3S or SWIS, our latest audio advancement, new specification released just last week. And today, in our final webinar of the series, we have Devon and John on hand to examine the growing suite of MIPI audio software specifications and tools. Just a few housekeeping items before we begin. You can download today's presentation from the Handouts tab on the right-hand side of your screen. In that Handouts tab, you'll also find a recently published MIPI technical brief entitled An Introduction to MIPI SWIS Audio Interface. That serves as a nice accompaniment to the yesterday's webinar. Today's webinar will run for approximately 45 to 60 minutes, targeting around 30 to 40 minutes of presentation content, followed by Q&A. Let me introduce today's speakers. So we have 2 experts here from MIPI. We have Devon Worrell. Devon is by day an audio architect at Realtek Semiconductor Corp. By night, he's a chair of MIPI Software Working Group, has been for many years. And accompanying Devon today, we have John Eklund. By day, John is a software architect at Cirrus Logic, and by night, co-vice chair of the MIPI Software Working Group and also co-vice chair of the MIPI Audio Working Group. So thank you, Devon and John, for being with us today to give the main presentation. I'll hand it over to you.
Thank you, Ian, very much. So I'm going to go ahead and do just a quick introduction of what we're going to cover today, and then hand it over to John to do a few, and then back to me towards the end of the presentation. So we're going to talk today about what is it we mean when we talk about the software framework, specifications in general, focus predominantly on the MIPI specifications that are actually adopted. They've been published and available. We'll go into detail on the overall system view, hardware and software. We'll talk a bit more detail about the device class for audio and discovery and configuration specifications, as well as talk a bit more about the audio features and capabilities, how that's reported and utilized, and go through the ecosystems that are out there today. And then at the end, we'll talk a little bit about what's coming up with new versions of specifications that are in development, and then hand it over to all of you for questions. And please, while you're seeing, you can put questions into the chat so that we can cover those later in the Q&A session. And with that, I'll hand it over to John.
All right, thanks, Devon. First off, what is MIPI audio software trying to do? The goals of the MIPI audio software specifications are to enable what's called an out-of-box audio experience. We want an OS vendor to be able to have standard drivers that works with any piece of hardware that a user might have in their system to enable a consistent user experience. The layered specifications that we've developed kind of permit phase-in. You can mix and match standard and proprietary pieces to allow the industry to transition from a legacy stack to a standards conformant stack. There's many layers to that. You've heard about several of the other pieces earlier in the week. Today we're primarily talking about the the audio functional specification, SoundWire device class for audio, and its various software dependencies. So what are those dependencies? MIPI SDCA talks about the audio peripheral functions. Those peripherals can be connected over, MIPI SoundWire or MIPI Swiss transports, and which transport is used in a system is fairly invisible to the SDCA function drivers. We also do have a pretty strong dependency on USB HID as a kind of a pass-through. It's used for things like headset buttons, can generate HID messages from an SDCA peripheral. If you have an SDCA peripheral with sensing, that can be interacted with as a HID device as well. So an understanding of that spec will help with some SDCA peripheral types. All of those things depend on what we call DisCo base. The MIPI discovery and configuration spec talks about the data constructs, the way that DisCo properties are structured, how they're stored in a system, and that is based pretty heavily on ACPI DSD. So that's the whole stack from an audio peripheral perspective. Folks have commented on, there's a new version of SDCA, which one should I use? The way SDCA hardware compatibility is kind of structured is that when there's a new minor release of SDCA, like 1.1 was recently adopted, every piece of silicon that was conformant to SDCA 1.0 is also conformant to SDCA 1.1. The new SDCA minor versions just add new optional features. They might change exactly how functionality is described, but they don't obsolete existing hardware or systems. So you don't miss out on anything by getting started with SDCA, knowing that there's a new version in the pipeline. Stuff that's in production now will continue to stay current. And also I should note that SDCA and discovery and configuration are both publicly available specs. So you can find those on the MIPI website. So the audio system view, there are pieces from many vendors in an audio system. So SDCA, as we've said, focuses on the audio peripherals and their drivers. So that's kind of the right edge and the left edge of this diagram. And in the middle, there's today some proprietary pieces. We do not talk yet about how those bits get out on the wire, so to speak. How the drivers on the host side talk to the transport. We'll talk about that later. But there's fewer SoC vendors than there are audio peripheral vendors, so that's a smaller proprietary driver surface than there was before SDCA. And yes, here's my highlights. This is the left and the right edge that I had just spoken to. On the right side, we have an audio peripheral that has some SDCA, audio functionality. Talks over transport to the SDCA function drivers provided by the OS vendor on the right. So we talked about audio functions. What is an audio function? An audio function is, an audio thing, a use case. It could be a microphone, a speaker, a jack. More complex ones or more abstract ones might be a Bluetooth radio that, has, a mic and a speaker connected remotely. It might be a display controller that can output, multi-channel audio over HDMI or DisplayPort. But all of these things, they have behaviors in common. And SDCA strives to standardize those behaviors. So like speaker protection on a speaker amp, or when you talk about a microphone with a smart codec can do, voice detection, it can do buffering, maybe it can do ultrasonic sensing. When you have a jack, button detection, we chose to use USB HID for, but that's a fairly standard behavior now. And the things that people do with jacks, like retasking, like between headphone and line out, or between line in and line out, things that every piece of hardware does, we provide standard interfaces to enable a standard driver. And standard drivers allow OS vendors and system integrators to enable common user experiences. So when you have a bunch of different SKUs in your portfolio, and those may have, say, jack codecs coming from different silicon vendors, the various systems with the various supply chains can have a similar user experience. Because all of the SDCA conformant hardware will have at least the SDCA mandatory minimum behaviors that are connected to SDCA mandatory APIs. Permits at a minimum a common subset of behaviors. And we'll talk in a bit about how those might be extended or customized. In between the SDCA functions and the host are obviously the audio transport. As I mentioned earlier, SDCA is fairly agnostic to whether those are SoundWire or Swiss. Indeed, the host drivers, the SDCA drivers in the host OS may not even know for sure what the transport layer is. One drawback, speaking of version dependencies right now, is that Swiss 1.0 doesn't have all of the DisCo description that a PC software stack would require. So SDCA Swiss peripherals will need Swiss 1.1. A thing that we hinted at on an earlier slide is that a single piece of peripheral silicon might have more than one SDCA function on it. That is enabled by an architectural feature called the multifunction driver. Multifunction driver is basically it's kind of a bus driver in the sense that it has child devices. So when there's a piece of SoundWire or Swiss peripheral silicon, that will enumerate with a multifunction driver that says, hey, this peripheral is an SDCA device. What SDCA functions does it have on it? And then it can enumerate the individual SDCA functions on the chip, which might be one, might be several. And then each one of those SDCA functions gets a class driver associated with it. This allows more flexibility in the class software. That you don't have to have a driver for every possible combination of things. They can be treated as sort of logically independent endpoints, even if they're on the same actual device. Each of those class driver instances can be extended. So we've talked about basic functionality. There's also basic functionality, optional functionalities handled by class drivers, and then extended functionality is stuff that the silicon vendors have added on. It might be custom, it might be novel, cutting edge, innovative stuff. Features that SDCA has not contemplated can be added via an extension driver, and the presence or absence of the extension driver necessarily gates whether the extended functionality is available, but it doesn't interfere with basic SDCA functionality of the part. So if somebody goes and uninstalls the extension drivers, then the basic class-driven behavior still works. And then we highlight the HID class stack here as another means of extension, because SDCA defines HID endpoints as basically pass-through. So anything you can do via HID, you can also do via SDCA without needing to do a custom driver stack or custom driver at all. A little bit more about options and extensions. So SDCA describes a fairly rich feature set for each type of device function. A lot of those features are optional because obviously not every peripheral needs to be a top of the line fancy version of a thing. So peripheral manufacturers can, choose not to implement optional functionality to reduce the cost or complexity of their hardware. The class driver can, recognize the capabilities of a particular piece of peripheral hardware and, adapt to what it provides. Um, that's in addition to the stuff that we never even thought about that you can add via extensions. Um, so the combination of a full featured class driver on the OS, and then SDCA mandatory minimums on the hardware, um, make SDCA a bit of a win-win. Audio peripheral vendors can do some interesting things without having to worry about integrating their drivers across a bunch of different OSs and host configurations, and system integrators and OS providers can ensure that their use cases are consistent in the way they want them, regardless of who their audio hardware vendor is. So we've talked about options. How does this class software know what the hardware is, what it does? And that's where DisCo comes in. So MIPI discovery and configuration is the standardized method that's common to used by many MIPI specifications, not just SDCA. But what it does is it provides a mechanism for standard host software to understand what a peripheral is capable of, without adding a bunch of cost on the peripheral itself. And we do that by storing all this information in BIOS flash, which is familiar to anybody who's worked with device tree or ACPI DSD before. We define a standard way for different peripheral vendors to describe the capabilities of their device. So then those descriptions can be modified by a system integrator, maybe because they're combining peripherals in a novel way, or maybe because they want to be more specific about the device capabilities or host software behaviors, and customize it for their particular system. Once those customizations are done, the ACPI source language, it's compiled and it lives in the BIOS flash, where host software can find it. And with that, I will hand this off to Devin to talk about the controller side and the system view.
Hi, thank
Thanks.
you, John. So in this end-to-end, at the moment today, there are host implementations, the quote manager, which owns the physical links. And traditionally, there will be a controller, which provides for your register reads and writes and for streaming of content. Today, these are all not yet standardized, and therefore in the software world, that's coming from SoC vendors predominantly, that to provide this functionality on the streaming, command and control, etc. Although all of the specifications that we've been putting together are laying the foundation for providing some standardization of this as we go forward in the future, and we'll talk a bit about that later. Within this same space, if you look at the all of the audio ecosystem and the framework, there are really almost two different aspects of it. One of it is I'll say the command and control. It's the ability to set the various functionality up, etc. And then there's streaming. In the case of SDCA, this whole streaming behavior is really defined today by the transport specs. So both SoundWire and Swiss are providing all of the capability that is necessary for payload transport, streaming audio data or other kinds of things. Those today are separate drivers from the functionality within the operating system. So the class drivers themselves don't actually get involved explicitly with the streaming behavior. That's provided as a separate driver stack that today is predominantly still making use of the SoC vendor host controllers to provide that functionality, but again, is not impacting the peripherals at all, the peripherals today are using the standard transport, data port, and streaming methods, and don't have to worry about what's happening within the on the host side of things. So we talked a little bit earlier about aggregation. If you look at how systems are being built, PC systems today, for example, in your notebook that's probably sitting in front of you now, you might have 2, 3, 4, 5, 6 different speakers. Very often, those are provided by separate actual physical devices. You might have 4 actual amplifiers that are actually driving, or maybe 2 stereo amplifiers that drive your left and right or top and bottom speaker transducers. In the systems, there's a need for that to look like one speaker. And so the SDCA itself actually provides a very full set of mechanisms for synchronizing so that you can stream and start and stop at the same time, as well as providing for mechanisms for what I'll call posture. That, for example, if you're in a tablet or a notebook and you rotate, your speaker positions for your spatial audio actually moves, and there are full methods built in to enable that behavior in the aggregation. Today, aggregation is provided predominantly by the operating system vendors, with some additional data coming from the integrator and the SoC vendor and the third party to provide the full ability to take speakers and or microphones, for example, microphone arrays, where you want to be able to take 3, 4, 5 microphones, use them together as an array for noise reduction, such as beamforming. The specs themselves provide a full set of capability for the operating system to take a look at multiple peripherals, multiple functions, which can be actually in different packages or even in different devices on different links. You could actually have an amplifier on one bus and another amplifier on another bus, and now you can actually put those together and make it look exactly like it's just one speaker within the system. So let's talk a little bit about what's going on in the ecosystems today. Windows Windows today had been predominantly using the specification and industry spec called high definition audio, HD audio. We are working with the MIPI specifications as a replacement for HD audio going forward, and actually hoping, as we mature all of the MIPI specs, to fully replace HD audio and move to SoundWire SDCA as the primary audio interface in all the systems. The Microsoft class drivers that are supporting SDCA have been around for quite some time, more than 3 years, and they are maturing and will continue to mature as we build new capabilities into the future versions of the specifications. Almost every single PC OEM today is shipping systems that support SoundWire and SDCA. It is predominantly being used in laptops. There's less adoption within the desktop space, primarily because there was more complexity in some of the legacy desktop capability. There is work going on, and I'll talk about it in a bit, in the future SDCA spec to provide some needed improvements to allow the more complex desktop configurations to be supported by the operating system. And you will expect to see that actually get that support fairly soon. So in Linux, there are upstream drivers that are available, again, predominantly for PC systems that are shipping with Windows as well as with Linux. There is good support for what we call the common SDCA functions. And SDCA, we didn't go into a lot of detail, but SDCA defines functionality for amplifiers, both those that are fairly simple or very complex that we call smart, Same thing for microphones. You can have simple microphones or much smarter ones that indeed might actually provide very full capability with low power autonomous behaviors. The universal audio jack, which is where you have your 3.5 millimeter jack support, as well as the ability to support what we call the simples, which can be even components that don't necessarily really support SDCA, but are provided support by putting appropriate information into the DisCo data. So you can actually take some legacy components and in almost every case make them look like something that is SDCA conformant and get class software support. So what is interesting about DisCo is that it actually is necessary to provide a fairly large amount of information about the hardware, the transport, the system and integration capabilities to allow you as an adopter or integrator or hardware vendor to build that data set. We have what we call a DisCo tool. The tool itself actually takes a template. The template is going to be provided like the specifications. So SDCA will have a template that is actually the full set of all of the different DisCo properties that are necessary to implement the spec. The hardware vendors and integrators then can take that template through the tool and actually update and provide input as to exactly what their hardware or system is supporting, which then generates intermediate files that then can be passed to the different vendors. The hardware vendor can be passed to the system integrator, which can be passed to the OEM. And in the end, that last file actually then gets compiled, and it creates the ACPI code that would then be integrated into the system BIOS as part of the system. So we're providing a very easy mechanism for building these tables to describe all of the various capabilities that are necessary, rather than having to build them by hand, if you will. So let's talk a little bit about where we're going with some of the specifications. Currently, the framework we talked about it was making use of SDCA version 1.1, SoundWire version 1.3, and Swiss version 1.0. Those specifications are currently being improved to provide some needed new functionality. And the SDCA 1.2 is very much focused on providing aggregation. So as we talked earlier, aggregation is being done predominantly by the operating system vendor, and it does not have a significant amount of customization and reporting available to the integrators and to the hardware vendors. SDCA 1.2 will provide a new set of DisCo data that will fully describe how all of the hardware in a system is routed and aggregated together. We're also looking at better support for desktops. There is a function type that is called retaskable jack that actually is there to provide the ability to have these 3, 6, or more 3.5 millimeter jacks that then can be used in various ways, such as being able to have a microphone input and line input, or change those to actual outputs so you could support multi-channel audio. And so we're providing that capability. Additionally, we're building in better support for interfaces like SPDIF and encoded content, so that the class drivers can now understand something more than just a PCM type of audio. It can support encoded content like AC3 or other Dolby interfaces. going forward. We're also ensuring that the combination of SDCA 1.2 and Swiss 1.1, which will introduce DisCo for the Swiss interface, that everything that's necessary for that combination to actually be fully supported. So the systems next year will hopefully be using SDCA 1.2, SoundWire 1.3, Swiss 1.1 as the foundation for what's necessary. So we talked earlier as well about the host side of the equation. So when you look at the systems today, MIPI has provided the standardization for all of the different audio types with speakers and mics and jacks. We've got great transports with Swiss and SoundWire, but almost none of the host side of that equation really had been supported. There is ongoing work today with two sets of specifications, one that is being provided within the software working group and another within the audio working group to fully standardize the host side of the audio framework. So these two specs are on the host side, Portal, which is a host controller standard that will actually finally standardize the streaming interface and all of the command and control, and provide the ability for class drivers to interface into all of the host hardware, which will also include the ability to talk to the SoC vendor's DSP or compute environments that are there. And that will layer on top of an audio specification for the host controller that actually will provide for the standardization for the managers. So together with all of these specifications, as they get completed later next year, you'll now have the specs and standards to provide a full end-to-end capability, meaning that the out-of-box experience, meaning that the operating system vendor can now ship class software that would fully operate every aspect of the audio framework without the need for any or requirement for any third-party drivers in the system. So this is the Nevada end goal that MIPI's been working towards. And as we do get all these specs in place, we'll provide a replacement for the legacy HD audio solution that we've been using up until now. And with that, I think I'll hand it back to Ian, and we can talk about Q&A.
Absolutely, yeah. So, well, we just on this slide, as you can see, put a slide together, all the various locations of the different resources have been mentioned throughout the presentation. So you can obviously get hold of the software specifications. They're all publicly available on the website. There's the direct links here. Yeah, if you can't find anything, then obviously reach out to admin@mipi.org. That'll be an email that will come through to myself, my colleagues, and we'll direct you in the right place. Okay, so yeah, let's jump to Q&A. So we've got some questions already submitted. I'll go through them in kind of a more logical order. So I think the first question I'll take is one related to slide 17. So I'll flick to slide 17 first. And then I'll put the question on the screen. I will read it out as well. So Devon, hi, on slide 17, I didn't understand streaming software. The baseline SDCA class driver enables basic audio functionality. What does streaming software provide?
Sure, thank you.
Yeah.
Oh, no, go ahead. Go ahead. Sorry. So streaming, we use the word streaming to really talk about the aspect of taking any kind of content, such as your music that you want to play to the speakers, and taking it out of host memory and putting it onto one of the links, SoundWire or Swiss, and providing it to the hardware that's outside. Everything that's necessary to actually do that streaming, and there are several types that are actually supported by the transport and by SDCA. The first is, we'll call it real time. That is, I have very low latency. I've got microphones. I want to process them almost instantly. I want to get the content as soon as it was captured off of the out of the air, or vice versa when I'm playing back. For example, if I'm a musician and I'm playing something, I want the total latency from me doing something on the microphone side to being able to hear it back out again to be perhaps as low as 10 milliseconds. And so there's mechanisms for providing the control for providing that set of data very quickly, indicating when it's ready, retiring it, and being able to recover memory, etc. All of that is of course needs DMA engines on the host side, and it makes use of the data port mechanisms in Classic and SoundWire and Swiss on the buses themselves. And so today, that host DMA capability is provided by SoC vendors, and each SoC vendor has their own method for doing that. And so therefore, that particular driver actually is something that's provided by the SoC vendor. There's an additional capability that's necessary there, in that, for example, if I have amplifiers on two interfaces, two buses, then you would need to take some content and actually maybe duplicate it or split it up and send it out on multiple interfaces, actually understanding that there are multiple peripherals and multiple buses being involved with the streaming. That is all part of the quote streaming driver capability. So it does have a piece of the aggregation, if you will, for being able to do fan in and fan out of audio content.
Okay, thank you, Devon. So let's move on. Next question relates to slide 18. Let me put it up on the screen here. Slide 18, are the microphones on the SoundWire bus, or are you envisaging more classical PDM interface connected to a Swiss converter chip?
So this is an interesting aspect in that, yes, indeed, both. Today, what we've seen predominantly in the PC space is rather than individual microphones, because the microphones today have traditionally been either PDM or analog. And so, and generally what we've seen for systems is there's usually a codec. And actually in the SDCA land, we call that a smart microphone function that supports multiple microphones. So you might have one package, if you will, that supports the 2 or 4 microphones on your PC. So it's already doing the PDM to SoundWire interface locally within the codec. Going forward with Swiss, one of the really key aspects about Swiss is that it is providing things that were really necessary to end of life or completely replace PDM and analog as a microphone interface. And so as we go forward, yeah, I would expect that we will end up with Swiss microphones that would be individual and then that would be aggregated. And so there wouldn't necessarily be a codec. You wouldn't have PDM or analog interfaces anymore. You would just have a number of native SoundWire microphones as we go forward. But I said, up until now, really, we've been taking the PDM and converting it in a codec to the SoundWire interface for use in the system.
Adds surround sound and encoded audio. Could you provide more detail on supported multi-channel audio formats? The SDCA spec I have seen only supports 2 channel left, right streams. And bonus points if you can say how this interacts with the optional direct render mode for amplifier functions.
Okay, so I'll talk about one piece of it, and then I'll hand it to John on the render direct. What we're actually building in, it's very correct that today SDCA generally basically said everything is stereo, and so that we had it much easier to be able to do some of this aggregation, etc. In SDCA 1.2, we are extending. There's a structure in DisCo that's called a usage map, and the usage map actually provides additional information about how a particular stream or data port can support formats other than PCM or PDM. And so in there is the ability to report that I need to transport encoded content, and that explicitly that content really can't be operated upon. It has to go kind of as a pass-through, if you will. And so that structure, along with the support in the data ports and additional reporting in 1.2, will allow the class software now to take, for example, AC3 is a good one in that on SPDIF today, you really would expect to be able to take AC3 from a movie player and pass it straight out to the SPDIF interface. And that is now done through a combination of reporting that there is this format supported within the peripheral, and controls that are actually provided in SDCA to tell the hardware, hey, I'm going to send you 32-bit opaque content that I want you to transport out. And so you'll see all of that capability being introduced in the SDCA 1.2. And John, you want to talk about Render Direct?
Sure. Well, both that and multi-channel. So when we talk about multi-channel in the context of SDCA 1.2 and desktop jacks, talk about those racks of 3.5 millimeter jacks in the back. That is sort of like logical surround sound. So there's a cluster or channel map that says, this is a 6-channel stream. It's got front left, front right, center LFE, etc. And those get routed by a multi-jack codec to the appropriate output jacks. The difference between that and Render Direct is that Render Direct talks about the equipment side of the channel space. So if you've got 4 amps in a tablet or a laptop, maybe they're top left, top right, bottom left, bottom right. Maybe you've got a subwoofer or center channel if it's a fancy laptop. The use of Render Direct is to let the host processor, like the SOC DSP, address each of those transducers directly, knowing its position in the equipment. And that SDCA feature is designed to be used in concert with some sort of spatialization engine running on the host, and that might be as simple as an AC3 decoder, or it might be a stereo image expander or some kind of fancy directional audio thing. So it's different but related. And Render Direct, as I think you've observed, is already defined in SDCA 1.0 and 1.1.
By the way, there's a key point here in that it is true that to provide the easiest method for class software to support audio is that SDCA and the ecosystem as a whole generally is working in the logical space. We are saying, hey, here's your left and right channels, and the equipment space, meaning that, hey, your left is actually on the top right because I'm in a tablet and I've rotated you. That is a separate space that is managed within the controls space in SDCA, so that the class software, generally speaking, doesn't have to have intimate knowledge. For example, where are the speakers and how do I manage the speakers if it's I rotate or I open a lid or close a lid or microphones come and go. That's all done very transparently in the SDCA control space by operating everything in the logical world rather than in the equipment or the physical space. And indeed, as John said, when you want to do these render type directs or capture direct, you are bringing that, you're requiring now that the host side actually now has intimate knowledge of exactly what's going on. Where is a microphone? Where it's pointed? What is its capabilities? Where are the speakers? How are they combined? If I've got a two-way speaker, which amplifiers are driving the woofer? Which one's driving the tweeters? And again, what happens if I rotate the tablet 90 degrees? And so it's a lot more complex to work at that equipment space. And so in general, we provide methods to do that. But then mostly you're assuming that there's going to be an integrator that's going to have to provide some very custom firmware or software to make that work.
are there any official certifications available for SDCA compliance? If I'm developing a smart microphone intended to meet SDCA standards, what strategies or safeguards can I use to mitigate the risk of non-compliance?
So it is interesting from a MIPI standpoint in that traditionally most of the MIPI specifications have had a separate specification outlining conformance, if you will, and giving information about how to do it. One of the challenges we ran into with the new style of these software and hardware specs, in that SDCA actually has requirements in place, not just on the hardware, but actually on software. Therefore, we found it quite difficult to provide a certification suite on the software side unless we were going to go out and find some vendors that could build specialized hardware to be used to validate the software. So what is happening, at least in the Windows environment today, is that, for example, in Windows, yes, there is actually a set of logo tests that come from Microsoft, and to mitigate your risk, essentially, one is, of course, that you do want to run your conformance against the transport. So if you're doing Classic or you're using Swiss, you do want to run against the certification suites that are going to be available in that space. But then after that, you really should be able to just build a system and plug it into a Windows system and run the operating system logo tests, because basically, if you can run against that test, you are pretty likely to not have any issues. And indeed, I think there's an expectation that the operating system vendors are likely to provide a set of requirements above and beyond, or maybe even subsetting those things that they might support from the MIPI specs, right? The SDCA may say, hey, you can do autonomous ultrasound. You can do presence detection using ultrasound. And it may be that the operating system says, no, we're not yet supporting that capability that's provided by the specifications. Anything you want to say, John?
No, I think that's it in a nutshell.
Okay.
Other than it's good, conformance testing is a question that's on our mind as well.
Yeah, it is, and it did. We've been thinking about, would it finally make sense to potentially still do some kind of a test suite where you would have to have some hardware that would allow you to have software that would run on the operating systems to validate the hardware. But again, from a standpoint of will you run with the class software, absolutely, we expect that just going forward that each of the operating systems will have their own sets of conformance, or in the case of Windows, the logo test, to tell you that you could be supported by their class drivers. Now, by the way, there is an ability within at least Windows today. There are methods where you can actually build custom drivers, although that's a negotiation with Microsoft and your customers as to whether or not they really would be accepting of a custom driver rather than a class driver plus an extension driver.
Okay, thank you. Next one, I think you covered this a couple of times, Devon, but to clarify, will SDCA not work at all with Swiss v1.0 and require v1.1? Will it work with some limited functionality?
I can take this one.
Okay.
Because this is actually kind of interesting. So, if you're a peripheral hardware vendor, you can make an SDCA peripheral based on the SDCA 1.1 and Swiss 1.0. The thing that's missing is the DisCo properties. So, a system integrator could not use that piece of hardware in a system with class drivers today, just because the transport layer DisCo specs didn't make the deadline basically for Swiss 1.0. So when Swiss 1.1 comes out, you would have to create Swiss 1.1 DisCo data for that SDCA peripheral hardware. So the reason I'm drawing that distinction, saying that the hardware can work on Swiss 1.0, is that if you're thinking about making a piece of SDCA, audio peripheral silicon, you can get started on it with SDCA 1.1 and Swiss 1.0. It just won't be it won't be commercially successful, or won't be usable in the market with class software until Swiss 1.1 is out with those DisCo properties.
And I will kind of chime in with a slightly different viewpoint as well, in that SDCA, fundamentally, if you take a look at hardware that you might build, there's really two pieces of IP that you might integrate into your devices that you'd be selling. One is SDCA, which I think is probably going to be a larger portion of your audio functionality, if you will. If I'm doing a microphone aggregation, smart microphone with buffering and ultrasound, it's likely that that's the dominant portion of your IP. All of that functionality is completely agnostic of the transport. Essentially, both Classic and Swiss provide equivalent functionality to provide everything that you would need to run that SDCA function, and to provide aggregation and synchronization. None of that is necessarily going to change in your hardware. So if you have a microphone and you're running on Classic today and you want to go to Swiss, you can do that. And I think that you could probably still manage to ship that if you needed to, with more custom environments, especially in an environment where you were doing your own custom drivers on the host side. And nothing necessarily would change with Swiss 1.1 coming out, other than the fact that there would be new data that's supplied into DisCo so that the class software can support that. But again, SDCA layers agnostically on top of both SoundWire and Swiss as we go forward.
Okay, thank you. Okay, next question. Obviously, Devin, you talked about the GUI tool. Is it available for SDCA 1.1?
So the tool itself is undergoing some improvements. There is a version of the tool it's available with. The tool, by the way, is and will continue to be pretty much agnostic of whether or not you're using it with SDCA or SoundWire or Swiss or I3C. It's a generic tool that basically takes a template. And so the templates themselves will need to be provided by each of the specs. The MIPI process is such that that will be what we call a supporting document. And no, there is not a template available for SDCA 1.1 yet, but that's something that we will be introducing shortly. And so in that particular way, the tool itself really doesn't matter. One of the things that we're doing with the tool that's more for spec creation is actually to build the template while we're doing the specification itself. But if you wanted to build your own template for any of these interfaces and use that with the tool, yeah, that is available today. Although I think really what we want is for everybody to make use of the templates as they're developed for each of these specifications.
Okay, thank you, Devin. I should know this, but Devin, where does one access the tool?
So at the moment, we are. It's a Git. It's a part of a project, a GitHub, and maybe John, you could speak to where we're going with it. I think in the end, we want it to be available, probably on Causeway, like we do with the specifications. But today, it's currently a software project that is housed in a Git repository.
Yeah. So right now it's a GitHub project in the same GitHub organization as the Swiss Visualizer. There's search for MIPI Alliance on GitHub.
Yeah.
And we'll be refining our distribution mechanisms going forward to make that a little more convenient for folks to download and use. Okay.
I didn't put a link on the resources tab, but if anyone wants that link, then just email us and we'll provide it to you if you can't find it. Great. Okay. And that's to ask how SDCA and DisCo dovetail with any open source initiatives that might be out there related to SoundWire.
John, you want
Sure.
to?
That is an interesting question. Um, there are, open source initiatives basically implement those. Um, any, the Linux SoundWire driver, at least on an Intel system, interacts with the DisCo data to determine the hardware capabilities. Um, Similarly, the Linux SDCA drivers interact with DisCo data to learn about the SDCA functions that they might want to work with. Without getting into the implementation details of ACPI on Linux, it's basically a dependency. As we mentioned before, the SDCA class conformant software on Linux is not as mature as the Windows versions. It's kind of trailing a bit. Linux development really takes off when there is real hardware in people's hands that they can work on. So it's closely following what is being produced and shipped by PC OEMs.
So it's probably time to wrap up. Any last points, remarks, John, Devon?
No, thank you for your time.
I'll just say that I am really, as the original creator of the audio specs that are the HD audio that has been in place since 2003, I think MIPI is finally going to provide a fantastic suite of specifications that to extend what's been available. And I would encourage everyone that's been participating today to join MIPI. There's some great work going on. I think there's opportunity for integrators and system vendors and hardware and software vendors, especially software vendors, as we look at providing capability with DSPs and things within the ecosystem to come and bring your value to our specification development. And with that, thank you again for everyone for joining.
Yep, I'll echo those words, Devon. Thank you, John, Devon, for presenting today, putting together this useful pack of information. And thank you, everybody, for tuning in today. And thank you for the excellent questions that were submitted. With that, I think we can draw this webinar to a close. Thank you, everybody.
Yeah.
Thank
Enjoy
you.
the rest
Have
of
a good day.
Thank you.